It is great to be here, and I'm very happy to see everyone who has participated in the project again. And well, for those of you who don't know, at the moment I'm working in tech as a computational linguist, and now I'm surrounded by all of these data scientists and machine learning engineers and so on. So I wanted to bring a bit of what I'm learning in that field to the study of ancient writing systems and show you a small experiment that I've done applying a natural language processing technique to a data set of geometric and archaic Greek inscriptions. As you will see, it's the kind of traditional, purely linguistic study about the abstract side of the writing system, as I mentioned today, and I'm going to make it even more abstract. But I hope that you will find this an exciting and refreshing mix that can contribute with new insights and methodologies to the field. So one particularity of the epigraphy of this period is the broad variety of alphabets that we find just to record the ancient Greek dialects. The individual characteristics of these alphabets and also their shared elements have been a research topic since the first half of the 19th century, when Kirchhoff published the first edition of his Studien zur Geschichte des griechischen Alphabets. Then in the 1960s, Jeffrey and Guarducci produced their own studies on the epichoric Greek alphabet. And at that time, doing this kind of research involved reading and analyzing hundreds of inscriptions only with the help of the human eye, multiple notebooks, and a typewriter. However, the computing power that we can access today means that with enough quality data sets, we can manage the ever-growing knowledge and evidence, run experiments that are not as time-consuming, and get statistical measures based on a myriad of data points that illustrate where our human intuition was correct and where those perceptions might be biased. Of course, this is not meant to say that all computer calculations are correct and we should trust them more than the insights of a knowledgeable researcher. On the contrary, as I will show today, our human perception is needed to identify the weak points of these computational techniques and where the data sets might be skewed. So here I will present an experiment that addresses the two main issues that the researchers mentioned above intended to elucidate. To start with, what are the most distinctive elements of each alphabet? And also, how can we cluster them in groups according to their shared characteristics? But to do this programmatically, first, we need to transform these inscriptions and alphabet into a format that a machine can understand and make calculations with, and that is numbers. That is the aim of NLP, or natural language processing, to represent human language in a way that can be processed by a computer and use computational tools to analyze it. For our purpose, I have used a simple NLP technique called TF-IDF, which stands for Term Frequency Inverse Document Frequency. This is normally used to identify the relevance of specific words within a given text and to measure the similarity between different documents. TF is a simple calculation of how many times a term or token appears in a given document divided by the length of that document, so the total number of tokens in the text. However, this measure alone would give a higher score to high-frequency words that are not, in fact, characteristic of any document, like articles, prepositions, or conjunctions. That is why we want to balance this count against the number of times the term appears in other texts, using its inverse document frequency. The final weight is calculated multiplying TF-IDF, and once this is done, we can join the scores for each word in each document to represent these texts as multidimensional vectors. So to illustrate this a bit more, let us imagine that we would like to measure the similarity of these three sentences so we can cluster them. The Cretan alphabet is a green alphabet, sorry. The Euboean alphabet is red, and Cretan is a Greek dialect. So if we calculate the TF-IDF weight for each of the words in each sentence, we can see how these numbers are quite low for words that appear in all sentences, like is, having an even lower score in the first sentence as it is longer than the other two. However, words that get repeated in the same sentence, like alphabet in the first example, or that only appear in one of them, like dialect, Euboean, Greek, and red, get higher scores, as these are interpreted as being more relevant in their text. Although this is a priori descriptive technique, that is, it only offers a description of the documents, the weights produced as a result of this calculation can be used to train predictive models for text clustering. However, to get to this next step, we first need to compare the vectors that we have produced here, used to represent these documents, and calculate their cosine similarity. That is, the measure of the cosine of the angle between two vectors. So following our previous example, if we make this calculation for all possible pairs and we rank them from most to least similar, we would get this result. The two sentences about the Cretan and Euboean alphabets are the ones which are the closest, followed by the sentences about the Cretan alphabet and the Cretan dialect. And finally, when comparing the sentence about the Euboean alphabet and the Cretan dialect, we get the lowest score. In this way, we are able to measure the similarity between the sentences and cluster them according to their main topic. Today's experiment, however, is not concerned with words, but with writing systems. So to put this a bit in context and following current theories in grapholinguistics, the base of a writing system is the conjunction of graphic elements with linguistic theory. Meaning that if we want to compare writing systems, we need to analyze not only the shapes of their signs, but also how these map with the linguistic elements represented by them. That can be called a graphematic relationship or feature. And in the case of these alphabets, of course, these signs render phoneme. But if we were to take the shapes or signs on their own, we would be doing a strictly graphic comparison, more similar to what Jeffrey and Guarducci did in their studies. However, the idea here is not just to know whether a zigzag sign has 3 bars in a specific alphabet and 4 in another, but also if that sign represents a sibilant consonant or a closed front vowel. And doing this comparison of the graphic and the linguistic elements all together across writing systems is the basis of comparative graphematics. So you can see how this is very different from the examples that I mentioned before with those 3 sentences, right? Because we know that in linguistic terms, graphemes and phonemes are not the same as words and meanings. The machine, however, does not understand this difference, and thus it will not process them differently if we present the data in an equivalent way. As when we're using the TF-IDF, we're just assigning values to each token in a string of characters according to how many times they appear in a set of tokens. So in our previous example, each word was a token, but here the data is displayed so that a single token renders both the shape and the represented phonetic value as seen in the original inscription. Even though it might be useful for other applications, in this case, the documents that I parsed through the TF-IDF vectorizer were not the individual inscriptions, but the combination of all graphematic relationships seen in a specific archaeological site, or where these cannot be traced down the region of origin of an inscription. By doing this, it is possible to compare the writing systems of each site or region as a whole, instead of analyzing these inscriptions individually. This information, the data, was gathered from a dataset that consists of 714 Greek alphabetic inscriptions dated in the 8th and 7th centuries BC, and it covers the graphematic relationships in each of them. This dataset also considers the notation of mid-open and mid-closed long vowels, and the use of digraphs for both vowels and consonants in a systematic way, unlike previous studies, which only consider those that have a corresponding letter in the Koine Greek alphabet. And well, all of this was recorded by taking the known phonemes of the archaic Greek alphabet and mapping them with the signs used to render them, represented through the same numbering system that I used in the experiment and that you will see in the slides today. So one of the elements that I tried to measure using TF-IDF are the most characteristic graphematic relationships of each alphabet. So those that can help us identify them best. The inverse document frequency calculation finds those that are not generalized across many of them, while the term frequency filters out possible outliers like phoneme grapheme pairs that may only appear on a couple of occasions. But the initial TF-IDF scores that I got are not comparable across sites, as those with very low numbers of evidence tend to give higher scores to each of their features, even if they are common across site. And this is what happens here, for example, in the case of Almina, where we only have one inscription that shows 3 letters, and as shown in the table, this gives a high score to what we could recognize as a common beta. So to avoid this, we can normalize the vectors so that they are all comparable. And to do that, in this case, I used the Manhattan or taxicab norm, which normalizes the length of the vectors. And well, that doesn't say much, but in the current experiment, that translates to considering each of the documents, so that is the evidence from each side, as if they had the same length. So this solved the issue mentioned above and offered a better representation of which could be the most characteristic graphematic relationships for each side, although in some cases it gives more weight to some exceptional cases. Some of those outliers are signs that appear only once in the whole data set, like the one you can see from Paros. In Monchimetos, some of the signs like numbers 55, 46, 34, and 29, or the theta with the dot in Pendescopia. However, most of the features that we can see in this table are representative of the sites where they are found. So probably a simple filter that leaves out the graphene forming pairs that are only seen once in the whole data set should be enough to solve the problem. Another interesting insight that we can derive from the TF-IDF scores is the closeness of this writing system. So by using the non-normalized vectors and calculating their cosine similarity for each possible pair, we can measure how similar these alphabets are in graphematic terms. And the interesting thing is that this method grouped correctly writing found in sites from the Sim region or in colonies under metropolis. That is the case of the Attica region, represented here by Athens and Monchimetos. Also, polis and sanctuaries related to Corinthia, for example, Corinth, Trachora, Pendescopia, and the colony of Corfu, or the connection of Eretria with its colonies Methone, Pieria, and Pekusai. There is also a cluster in Boeotia that links the region to Tanagra and Thebes, and another group is found around some Cretan sites like Treros, Cortina, and Patrati. And finally, well, the Samos and Sperna pair also comes as no surprise, since these are both Ionian sites in Asia Minor. So given that there was no parameter in the data that would give a higher weight to pairs known to have a geographical or colonial connection, these obvious pairs should be seen as a confirmation that the algorithm makes predictions which are coherent to what we as researchers can perceive from the epigraphical evidence. Yet, not all of the results were as predictable. In Rhodes, for example, there seems to be no cluster of alphabets between sides. In fact, Ialisos is paired with Ephesus, while Camilos is paired with Athens and Monchimetos. In this case, I think we might be looking at a problem derived from not having enough evidence for these sites. As you can see, I could only record a few graphematic relationships that could be reconstructed from the inscriptions found there. And it's probably the Eta in Ialisos that brings it closer to Ephesus. However, Camilos could well be in the same cluster if only we had we had evidence of how they notate their mid-open long vowel. And these might indicate that the algorithm has some bias towards alphabets with high evidence, such as that from Athens, which has almost 200 tokens. And we should be aware of that when interpreting these results. The case of Commons, though, is quite an interesting one. This commercial site in southern Crete shows some graphematic elements that could be related to other sites in Crete, for example, the use of eta. Well, others seem to be related to sites outside of the island, like the Strait Island. In the table with the highest similarity scores, it appears first related to Montimetos, another site where we find features from different alphabets, then to Methone in Pieria, Pithecusae, Athens, and Eritrea. Given that the evidence for Cretan, Attic, and Euboean sites seems to be reliable, as discussed earlier, this suggests that overall the writing found in Commons is closer to that of Attic and Euboean polis and Ptolemy. However, since there are still some graphematic features found in this site that seem to contradict this link, like the eta, perhaps we would probably benefit from doing an analysis that would indicate the similarity per inscription rather than for the alphabet, like the writing in Commons, found in Commons as a whole. Another interesting case is that of Sikinos and Thira, as a pair with a quite high similarity score. If we look back at the most characteristic letters in Thira, we can see that it is the consonant clusters and the aspirated consonants that could be the best way to recognize an alphabet similar to that of Thira. Even the sign for the voice stop B could be a very good sign. However, there is no record of how any of these sounds were represented in the writing of Sikinos at the time. Probably the connection is in the other signs, which on their own might be common to other alphabets as well, but this exact combination seems to draw a link to Thira rather than other Cycladic islands or even Crete. And this is an important lesson about how we have been clustering alphabets before and why it only took us this far. Researchers have focused more on specific letters and how they divide the epichoric alphabets in major groups, like the sigma users versus the san users, those that have specific signs for long vowels or for consonant clusters, etc. Nevertheless, it seems that it is the overall combination of graphematic relationships that tells us to what extent different alphabets might be related or not. But of course, analyzing these patterns in the epigraphical record of 67 archaeological sites, as I did in this experiment, would be quite time-consuming. However, using computational tools, we can get fast results that we can use as useful suggestions. As you can see, there are way more pairs that we could look at and comment. Yet I chose to show only the highest scoring pairs. not just because we're trying to look at similarity rather than dissimilarity, but also because the lowest scores are not as reliable. These do not necessarily suggest that two alphabets are not alike, as the sites with very small epigraphical evidence show scores closer to 0 across all pairs. And that happens, for example, in the case of Almina and Paros, which only count with 3 and 4 tokens, respectively. This means that to have a reliable dissimilarity measure, we would need a dataset with enough evidence for each site, or even to ignore low evidence sites in experiments. Still, I find that these and other computational techniques have a lot of potential to help us manage and process big amounts of data. Even though these experiments do not come without problems, our human knowledge helps us recognize biases and gaps in the dataset and find solutions to them. I have already mentioned how outliers and unbalanced datasets can produce skewed results. But identifying where the bias is makes it possible to filter out any unreliable data for future experiments. While the results of what I have shown today were for the most part unsurprising, I take this as a sign that the experiment actually worked, since the measures seem coherent with our intuition as researchers. Still, some results did bring interesting insights about some connections that have been overlooked in the past, and that even question the way in which we have approached the problem so far. It would be really exciting to see in the future how these data sets expand and even get improved to be able to make more applications out of NLP techniques. For example, just with what I have shown today, it would be possible to train a machine learning model on every single description so that it can learn from their place of origin and later predict the most likely alphabets for inscriptions with unknown provenance. Of course, all of these could be even extended to different chronologies or for the comparison of other writing systems. However, that would mean creating the necessary data sets to run the experiments, and that would imply a whole new project in itself. Gathering and digitizing the data is the most time-consuming part of any digital humanities project. But if we make the data available and design our data sets in a reusable and accessible way, researchers all around the world could run their own experiments and the field could advance rapidly. At least the dataset and all the code that I used for this experiment will be available online so that anyone can replicate the experiments and get the complete results, to analyze them, and even build upon this to create new applications. And now I am looking forward to your questions, and I thank you for your attention.